practice two-dimensional vectors, we really need to spend the rest of our time on 3D vectors. 3D vectors, we need a 3D coordinate system. It's got to be a right-handed coordinate system. There are a couple of options, but our book has chosen to put the X and Y plane down flat on the ground and have the Z direction pointed upward. So now if I have a force vector F in our three-dimensional world, I need to write it using both an X, Y, and now also a Z component. So my force vector would need to look like Fx in the I direction plus Fy in the J direction plus Fz in the K direction. Now, if we can get it written like that, then the rest of the math is pretty similar to what we do for 2 dimensions, right? If I needed to find a resultant, all I need to do is the X resultant is going to be the sum of F1x plus F2x plus however many forces you have. You just add up all their X components. Your resultant in the Y would be the result of adding up all of the Y's, and your resultant in the Z would be the result of adding all of the Z's. Then once you're done with that, you might need to find the magnitude, and the magnitude would be given as by square rooting our x squared plus our y squared plus our z squared. It's like Pythagorean theorem in 3 dimensions. You just sum up all the squares and square root it, and that will give you the overall magnitude of your resultant vector. Now, as far as determining what direction it acts in, we need to do a little background here. There are 3 different ways that we specify directions in 3 dimensions. One of them is called direction angles and direction cosines. This is, I think, the most friendly of all of them. Put some Cartesian coordinates up here. We've got x coming out at us, y to the right, and z upward. Let me draw my force vector F again. And what direction angles and direction cosines mean is if I know the angle from that vector directly to the x-axis in 3-dimensional space, we call it alpha. The angle between F and the y-axis we call beta, and the angle between F and the z-axis we call gamma. So alpha, beta, and gamma are what we call the direction angles. And here's what's cool. If I have the direction angles, I can find Fx, Fy, and Fz really fast. Fx is simply going to be F cosine alpha. Fy is simply going to be F cosine beta. And Fz is simply going to be F cosine of gamma. So if I know those angles, it's really easy to find the components. Let me show you just in the y direction why this works. My vector F is 3-dimensional. So if I were to drop a projection straight down into the xy plane, I am going to end up with a component in the x direction, a component in the y direction, a component in the z direction. And in fact, my components are actually shown on the picture with how I just drew that. This side right here would be my y component, this side would be my x component, and this side right here would be my z component. So I need to figure out how long each of those are. Well, it turns out that if I can make a triangle right here, and in 3D, the right angle side doesn't always look like a right angle because this is actually coming out of the page at me a certain amount. But that triangle that I end up with, if I take the vector F and I kind of drop its projection onto the y-axis, this is actually my right angle. This is the hypotenuse of the triangle. This is the side we're trying to find. That would be my Fy component. And can you see the side I'm looking for is adjacent to beta. So that's why I use cosine of beta times the hypotenuse. So back to what we just did, if your magnitude can be found that way, we can actually indicate the direction of our resultant vector by using these direction angles. So the way we do that is I'm going to solve for cosine alpha, cosine beta, and cosine gamma. Those are going to give you the direction. And this is actually really easy to do. You simply take Rx over the overall magnitude R. This one's Ry divided by the total magnitude R, and this one will be Rz divided by the total magnitude R. And then you can take the inverse cosine if you actually want the angles themselves. In 3D, to get direction, we're going to use these direction angles. There is one little trick about direction angles that I want to show you, because sometimes in the book, they're going to give you 2 of them, but not the third one. And the reason is, if you know 2 of them, you can find the third one. And here's why. So if I have a force vector F that has been written in terms of its direction cosines, well, let's go find the magnitude of that F. Magnitude of F will be the square root of fx squared, that's f cosine alpha squared, plus fy squared, that's f cosine beta squared, plus fz squared, that's f cosine gamma squared. All right, let's simplify that. We know that has to equal f, but let's actually simplify the math. That means if I pull those f squareds out of the square root, this is equal to f square root of cosine squared alpha plus cosine squared beta plus cosine squared gamma. Well, the only way that that can equal f is if this guy under the square root must equal 1. So if I know alpha and I know beta, then I can use this set equal to 1 to solve for gamma. All right, let's do spherical coordinates next, which I have also heard called the blue triangle method. You draw a picture, x is coming at us, y to the right, and z is up that way. In this case, let's say I have a force vector F, and let's drop a vertical straight down into the XY plane, drop a perpendicular down. What we are sometimes given are these two angles. I'm going to shade these triangles in with a couple different colors. Let's make this vertical one green, and let's make the horizontal one pink. They're both right triangles, and you're sometimes given the two angles. This angle right here, call it theta 1, and then this other angle up here, we'll make it green, call it theta 2. These are not direction angles. It's literally spherical coordinates, which means one of the angles tells you how high are you elevated above a flat plane. The other angle tells you what is your orientation or your bearing within the plane. The way I like to solve these is with two steps. I like to treat these as two totally separate two-dimensional triangles. And what I'm finding is this leg and this leg of the first triangle. This side happens to be your z component. This side is not your x or your y component. I like to call it the horizontal component. So let's use that green triangle and first find out from the green triangle that the z component would be f sine theta 2 because this side is opposite theta 2. And the hypotenuse is f. Now let's find the other leg of that triangle. Call it the horizontal side. It's going to be f cosine theta 2. And we've got the horizontal and vertical components from the green triangle. Now we're going to go use the pink triangle. Now for this pink triangle, the hypotenuse is f horizontal. So when I take the side that's adjacent to theta 1 with how my picture is drawn, you have to actually look at the triangles and which angle is given to do these. This is going to be my y side. So when I use cosine theta 1, I'm going to get the y side. So my y component is going to be not f, but f horizontal, because that's the hypotenuse of the pink triangle, times cosine of theta 1. And then finally, fx is going to be negative, because it's pointing in the negative direction. It's going to be also f horizontal times the sine of theta 1, because x is this direction, and so my component's pointing back that way, and the hypotenuse of my triangle is fh. If this is helpful, feel free to draw two-dimensional triangles. What I've got is f, this side would be f horizontal, this side would be fz, and here is theta 2 in my picture. And then for the pink triangle, the hypotenuse is fh, this side is fy, this side is fx, and there is what I called theta 1 in my picture. So using two separate triangles, they have two different hypotenuses. So if you want to then go write your f as a Cartesian vector, my x component will be minus fh, which is f cosine theta 2. So I'll have minus f cosine theta 2 sine theta 1 in the I direction. Now for the j direction, I need fy, which is fh times cosine theta 1. So I end up with f cosine theta 2 again, because there's my fh, times cosine theta 1 in the j direction. And then finally, the z is just f sine theta 2 in the k direction. Okay, this one is the hardest for students, absolutely the hardest for students. And there's a whole bunch of things that makes it hard. I feel like if you color code your triangles and actually draw them out as separate pictures, so you're noticing that the hypotenuse of this triangle is actually one of the legs of the other triangle, the pattern will always be this way. Your z component will simply have an f times a sine or cosine of a single angle in it. And your x and y are always going to have a sine or cosine of two different angles sitting in them. And the pattern is, if we had sine of theta 2 here for z, we're going to have cosine of theta 2 in both the x and y, because that gets you your horizontal component. And then you'll have a sine of theta 1 and a cosine theta 1, making your i's and j's different. As a double check, if you ever wanted to make sure that this works out, you could check the magnitude. It's got to be the square root of, you'll end up with an f squared in every term. So you can pull the f out in front. Inside, you should end up with cosine theta 2 sine theta 1 squared, this has a minus sign, plus cosine theta 2 cosine theta 1 squared plus sine theta 2 squared. Okay, if you work that math out, it needs to end up equaling f. F times that square root of stuff needs to equal f, and it will if you've done the math correctly, because you remembering the fact that sine squared plus cosine squared of the same angle is 1. So if you take these first two terms, you can factor out the cosine theta 2 and you end up with sine theta 1 squared plus cosine theta 1 squared, which is 1. We'll be left with the cosine squared theta 2, which when you combine with the sine squared theta 2 is also 1. Finally, my favorite is when we're given the dimensions. Picture looks like this: x, y, z, and we are given that here is our force vector F, and it is oriented so that maybe it goes along a rope or something. And somebody tells us the lengths of all of these sides. They tell us that this side is A, this side is B, and this side is, right here is C. They tell us that to get from maybe the origin to the endpoint of a rope that has a force directed along it, you have to go this distance in the x, followed by this distance in the y, followed by this distance in the z. What I like to do is actually think of this as 3 separate vectors. First, I'm going to write what's called a position vector. We're going to use a lowercase r for that takes you from the origin to the end point of the rope. This is a force along a rope. We're going from here to here. So the position vector would be you go a inches in the I direction, plus b inches in the j direction, plus c inches or meters or whatever in the k direction. Next, I want to turn that into a unit vector. Because the problem is, if a, b, and c had units of inches, now my position vector has a magnitude which is not 1. It has a bunch of inches to it. So to do that, I take my position vector and I need to divide it by a number so that it becomes a unit vector. Well, that's easy. You divide it by the magnitude. Divide it by the square root of a squared plus b squared plus c squared. That might be better to write out this way. A over square root of a squared plus b squared plus c squared I plus b over the square root of a squared plus b squared plus c squared j plus c over the square root of a squared plus b squared plus c squared k. What I've done is first I had a position vector. That's a vector with length units that tells me how do I go from point A to point B. How far do I have to go? Now I divide it by the length, so I get a little unit vector that has the exact same direction, but only a length of 1. So finally, now if my force had a magnitude of 100 pounds or 100 newtons or something, I can now write my force vector in Cartesian coordinates as follows. It has a magnitude F and a direction of a over square root of a squared plus b squared plus c squared in the I direction, b over square root of a squared plus b squared plus c squared in the j direction, and c over the square root of a squared plus b squared plus c squared in the k direction. Now that looks like a lot of math, but in practice, this is one of the easier ways to get your vector because we're just looking at lengths and dimensions on a picture. You get a position vector first. You divide by the magnitude to get the unit vector, and then you multiply by the magnitude of the force to get a force vector, where here is your magnitude, and then the stuff inside of the brackets is the direction. So there's a synopsis of how we get vectors into Cartesian components in 3D. That's going to be the end of this video. What we're going to do next time is just work a whole bunch of practice examples using all of these different methods.